Since time immemorial, humankind has looked to the stars. The universe has always been a source of fascination and of mystery. How was the cosmos born? What else might the universe contain? And where do we come from? The Sun lies at the center of our planetary system. It is a cosmic source of energy, a massive nuclear fusion reactor some 4.7 billion years old. Beneath its surface, 600 million tons of hydrogen are converted to helium each second at a temperature of 15 million degrees Celsius. From the surface of the Sun, light and heat travel into outer space and to Earth. Welcome to Spacetime, featuring astronaut and scientist Ulrich Walter and an expert on surprises the universe has in store for us. The Sun. Without it, there would be no life on Earth. The Sun is the star that sustains us, supplying our planet with warmth and light. But in the end, the Sun will destroy the Earth. The life made possible by the Sun will be wiped out inexorably and irrevocably.
Our Sun, we need it to survive. We need its energy. But the Sun is slowly growing hotter, and eventually it will destroy us. Temperatures here on Earth will soar to over 100 degrees Celsius. The Earth's oceans will evaporate. The Sun will swell, growing ever larger until the outer layers finally reach and then envelop the Earth. And then it will explode and die. That, of course, will spell not only the end of our solar system, but of humankind.
The history of our Sun begins with the Big Bang nearly 14 billion years ago. In this cosmic dawn, space, time, and matter, the universe itself was born. Just fractions of a second after this creation, tiny elementary particles were formed. These became the building blocks for hydrogen and helium, the lightest elements. The young universe continued to expand. The cooling of the universe, along with gravity, helped transform this matter into the first galaxies. As vast clouds of molecular gas continued to increase in density, the first generation of stars was born. Very large and very hot, the first stars died young. They existed only tens of millions of years before they collapsed. These supernova explosions then dispersed the elements that would become the next generation of stars. Born about 8 billion years after the Big Bang, our Sun was also formed out of matter that a dying star had hurled into the universe.
The Sun fascinates me for various reasons. For one, it's a key to understanding the many billions of other stars in our cosmos. They're all similar to our Sun. The Sun is an ordinary star, but the only star we can unlock. The only one we can study and understand in detail many of the physical processes that also take place in other stars. And of course, the Sun is our star, the star of our own solar system, which has given us life.
The energy of our Sun shaped our planet over billions of years. It determined our climate and our seasons.
For me, it's a very interesting star. It's right at our front door. You can see its diameter. Unlike the other stars, you can see it's not just a little speck. You can see the disk, the sunspots, and the sun shines onto Earth. That's key. It's the source of our energy. Without the sun, all life here would perish.
The Earth was also formed out of the same material that created our Sun. Dust and small particles clumped together to form new celestial bodies, which continued to grow. The heaviest elements became planets.
There are places in outer space that are somewhat denser than average, that have more gas and dust. Under certain circumstances, these interstellar clouds, as they're called, can collapse under their own weight. That's how stars are born. One of them is our Sun, which emerged some 4.5 billion years ago.
Our planetary system was created by the same cosmic catastrophe that gave rise to our Sun, a supernova. Such explosions ensue when a massive star collapses and explodes. These brilliant bursts of light in outer space mark the death of a star and the birth of new celestial bodies. The explosion sends an enormous amount of matter hurling into outer space. Along with hydrogen and helium, the expanding cloud of gas and dust is comprised mainly of oxygen, carbon, silicon, and iron, the basic building blocks of planetary formation. Such clouds of gas and dust can collapse under their own weight. Sometimes they are compressed by a new shock wave. At the center of the cloud, an area of high density begins to form. It attracts even more matter, becoming the cradle from which a new star is born.
How did our solar system come into being? Well, it's part of an enormous galaxy that we call the Milky Way. So let's take a look at the Milky Way. There it is. Well, that's not entirely correct. That's what we call galaxy M31. But we know it looks pretty much exactly like our Milky Way, which, by the way, contains about 100 billion stars and has a diameter of approximately 100,000 light-years. How was this Milky Way born? We know that in the beginning, there was an enormous cloud of gas that was far larger than what we see here. At some point, dark matter moved into this area, drawing this visible matter in its wake. As a result, this cloud of gas condensed into this area we see here. At the same time, the gas cloud began to rotate and collapsed to form a disk. That's exactly what we see here. There are no stars yet. Every once in a while, though, there was a supernova which generated an explosion. The ensuing shock wave then caused certain areas of the gas to condense. That's where the stars were born, one of which was our Sun. So, where's our Sun located in the Milky Way? Very roughly speaking, on the outer edge, about here in our Milky Way. Is it a coincidence that this spot is where life emerged? No, absolutely not. Had our Sun been situated closer to the center, for example, we know that life wouldn't have emerged. There are so many supernova explosions in that region that any life would have been extinguished right away. We wouldn't have lived very long. On the other hand, if our Sun had emerged outside over here, that's an area where there are no heavy elements, meaning elements such as carbon and iron, which make up our bodies and indeed the Earth itself. There would be no planets over there, so there couldn't be any life. There's just a very narrow strip, the so-called habitable zone, where there aren't many supernova explosions and where planets could emerge that could sustain life. So you could say that we got very, very lucky.
The first prerequisite for the birth of a star is a random conglomeration of matter in outer space. The cloud of interstellar matter collapses under its own gravitational force. The initial rotation causes the smaller area to move outward, where the orbiting planets will form. The much larger part of the cloud gradually moves to the center, where its mass and density continues to increase until it becomes a pre-stellar core. As its density increases, the temperature inside this nascent star rises too. Pressure and temperature continue to rise, a process that takes about 100 million years.
An enormous fusion reactor is formed. In a fusion reactor, hydrogen atoms collide with such force that they fuse together. As soon as this nuclear reaction is triggered in the core, we can say a star is born.
The star has ignited and burns. With core temperatures of up to 15 million degrees Celsius, hydrogen fuses to become helium. The sun then emits this energy into space in the form of sunlight.
When energy is produced inside the sun, it takes 1 million years to reach the surface. In some of the smaller spots, you might not notice anything for 100,000 or 200,000 years. So this ignition is actually a very mysterious and silent process, which takes many years to become apparent.
The photosphere is the visible surface of the sun. It is about 400 kilometers thick and just under 6,000 degrees Celsius, comparatively cool. The next two layers of the sun's atmosphere are the chromosphere and the corona. Inside the corona, the temperature rises once again to several million degrees Celsius, a phenomenon that scientists still don't fully understand. But they do know a great deal about the spots on the surface of the sun.
Sunspots are relatively easy to observe through the telescope. One very significant advance came when Heinrich Schwabe, an amateur astronomer, had a telescope set up in his apartment. He ran a pharmacy, which was on the ground floor. And every free moment, when it was light outside, he ran upstairs and observed the sun. He diligently recorded the sunspots, day after day. After 20 years of painstaking work, he plotted them out on a diagram. That's when he noticed, oh, the number of sunspots isn't always the same. Sometimes there are more, sometimes less. That's how he discovered the solar cycle, the famous 11-year solar cycle, which was a major advance.
Sunspots appear and disappear again. They're an indicator of the activity of the sun. These dark spots were first observed more than 2,000 years ago. The sun. Countless generations have revered or even feared it. Many believed a solar eclipse was an ill omen, heralding the plague, death, or the end of the world. The sun was worshipped, venerated as a deity. Humans were sacrificed in its honor. In some cultures, the sun was regarded as the creator of the world. Its path across the heavens was carefully measured and observed. The sun determines the cycle of day and night and influences our climate. Its light and warmth is what allowed human life to emerge.
The sun has always fascinated us. The first people who observed the sun, or observed it more carefully, were often astrologers. They wanted to predict the future based on the position of celestial bodies. But it wasn't until the invention of the telescope that people embarked on rigorous observation of the sun.
Humankind has a primordial desire to explore and explain our world. The philosopher and scientist Aristotle propagated a geocentric theory of the universe, under which the Earth constituted the origin and center of all existence. The ancient Greek philosopher Ptolemy also believed that the Earth was at the center of the universe. That belief held sway for nearly 1,500 years. Then Nicolaus Copernicus realized that the sun was the central point around which the Earth and the other planets in our solar system revolved. His theories were not confirmed until a revolutionary invention arrived on the scene: the telescope. Galileo Galilei was the first scientist to turn a telescope to the heavens. He discovered the 4 largest moons of Jupiter. And he was the one who realized that the Milky Way was not simply a nebula, a cloudy mass, but a cluster of stars. Galileo also described the spots on the sun. This marked the birth of modern astronomy and the beginnings of scientific research on the Sun.
The Sun is simply too large. I can't bring it into my laboratory. It's too hot. I can't go there and bring back a piece. It would burn our probes to a crisp. But we can carry out direct investigations on one part of the Sun by going to outer space and capturing a piece of solar wind. That's being done.
The solar wind is a stream of charged particles released from the Sun's surface. This wind can become a veritable storm. The surface of the Sun is a seething cauldron whose matter is in constant motion. Much as here on Earth, the rotation of the molten Sun generates enormous magnetic fields which form tangled loops. When these loops break away from the Sun's surface, they release intense bursts of energy which can result in the ejection of huge quantities of matter.
Seen from here on Earth, the Sun looks quite harmless, but it really packs a punch. It generates gigantic eruptions. You can see it clearly here. An enormous mass is just being torn out of the Sun. By the way of comparison, the Earth's diameter is only about this big, so this is huge. These ejections emit a huge amount of gas. It's comprised mainly of protons or subatomic particles with a positive electric charge. They're ejected from the Sun at an enormous speed, several hundred kilometers per second, toward Earth, for example. If the Earth's in the way, it will be hit by this radiation. But if it's somewhere else, say here, or over here, it will be spared. But just imagine all this mass is plowing toward Earth at an enormous speed. The blast of the energy can be 1,000 times higher than normal. It hits the Earth at the north and south poles, because that's where the planet's magnetic field directs those geomagnetic storms. That's why we see those spectacular northern and southern lights there.
Depending on its intensity, this solar wind can affect the Earth's magnetic field. The floods of electrically charged particles head towards the Earth's magnetic poles, where they can give rise to a stunning natural spectacle called the auroras, the northern and southern lights.
This electromagnetic radiation is dangerous here on Earth. We don't notice it in our day-to-day lives because it's fairly infrequent. But in 1869, a powerful solar storm hit the United States. Back then, they had nothing like today's high-tech infrastructure, with the internet, the electric grid, and so forth. But they did have telegraph systems, which failed as a result of these solar flares, as they're called. The auroras were visible across the entire United States.
When many billions of tons of plasma gas are ejected into the solar system, these electrically charged particles can trigger a powerful geomagnetic storm.
Experts now worry that our hyper-networked world makes us vulnerable to these extreme fluctuations in solar activity. In the future, we might want to pay attention to what the Sun is up to.
In the worst-case scenario, a solar storm could cause power surges that would blow out the electrical grid.
We've now realized that our entire infrastructure is vulnerable. The more we rely on the internet and networks, the more vulnerable we are at those points. There's nothing we can do about it. We can't switch off the sun, but we could devise an early warning system, much like a weather forecast.
Satellites have a major impact on our daily lives. We live in a digital world. Our communication systems and our entire infrastructure have become dependent on a continuous stream of data, much of which is transmitted by satellite.
Satellites would be the first things to suffer a hit. We need to make sure our navigation satellites aren't affected. To prevent damage, we might need to take these systems offline till it's over. Of course, we'll also try to build more stable systems which are less vulnerable to these events we can't control. But if we realize something's headed our way, we need to shut down these systems, and when it's over, we can restart them.
Nowadays, the Sun is observed and monitored around the clock, both from the Earth and from probes in outer space. In 1995, ESA and NASA launched the Soho Scientific Observatory. The spacecraft delivers images of solar eruptions in real time. The Soho satellite carries a large range of instruments on board, which can be used to study everything from the inner core of the Sun to its outer corona. The data gathered by the satellite is also exceptionally high in quality.
Before Soho, the Sun was a rather boring, static star. We knew that it had several layers, and we knew it had occasional eruptions. But thanks to Soho and the instruments that followed, we know that the Sun is constantly bubbling. There's always something exploding somewhere on the Sun. It's never quiet, never. We've been forced to completely overturn our understanding of the Sun. It's all thanks to Soho.
The Soho mission is now more than 20 years old, but it's still one of the most important satellite observatories providing data about the Sun.
So where does this probe need to be to have the best possible view of the Sun? Well, it needs to have the same angle of view as the Earth, and to be able to communicate easily with the Earth. As it happens, there's an excellent spot for that between the Earth and the Sun. Let's take a look. Assume this in the middle is the Sun. 150 kilometers away is the Earth. To have the same angle of view, the Sun needs to be near the Earth, and it needs to be able to communicate easily with Earth. And for that, it will need to be located at a specific point. If I draw a line of connection from the Sun and the Earth, that point will have to be situated on this line, at about this point right here. It can't be too far from the Earth. It's about 1.5 million kilometers away. This point has other beneficial characteristics. It's called the L1 point, or the first Lagrange point from Earth. Lagrange was an old French physicist who demonstrated some important aspects of this point. For example, when I position a probe there, it stays there. It won't keep moving. That's nice, because I won't need fuel to maintain the probe in that position. But this point also has a major disadvantage, which we'll examine from a different perspective. If I look toward the Sun from a position on Earth, the probe would be visible right in the middle of the Sun. I'm standing on the Earth here, looking toward the Sun. This is an enormous disadvantage, because whenever the probe communicates with me, the signal would be drowned out by the Sun's radiation. I wouldn't be able to hear or see anything coming from that probe, so the probe needs to be moved slightly off-center. This L1 point has another lovely aspect too. It has what is called a halo orbit, meaning an orbit that circles this point. I'll sketch that right here, positioning it not in the middle of the Sun, but outside it. If I direct my antenna at this orbit, I can communicate with the probe, but the probe will still have a very good view of the Sun. That's what's so wonderful about this L1 point, and that's why Soho is positioned there.
The European Space Agency's new Solar Orbiter mission will also study the Sun. ESA's satellite will also help us better understand the impact of the Sun here on Earth. One of the Solar Orbiter's tasks will be observing solar wind and space weather.
The Solar Orbiter will leave the Earth's orbit. It will then follow its own very elliptical orbit around the Sun. On one side, it will be quite close to the Sun, and on the opposite side, it will be further away. And it will leave the Earth's elliptical orbit, the Earth's orbit level. The Solar Orbiter will be able to observe the poles of the Sun through its telescopes, which will also be a first.
The mission has been designed to deliver new data about the star at the center of our planetary system. For the first time ever, observations will be carried out of the rear of the Sun. The instruments on board the solar orbiter will generate a 360-degree image of the Sun's magnetic field. It's hoped that the data provided by the mission will help scientists better understand the inner workings of the Sun and the impact it has on the Earth and other planets in our solar system. The Max Planck Institute for Solar System Research in Göttingen, Germany, is taking part in the mission. The institute conducts research on a range of topics involving the Sun, the heliosphere, and solar winds. This research isn't only being conducted by satellites. With their Sunrise project, the Göttingen researchers are breaking new ground. Sunrise is a balloon-borne solar observatory. Many of the Sun's secrets are contained within the ultraviolet radiation that it emits into outer space. On Earth, however, our atmosphere absorbs the majority of this ultraviolet radiation. As a result, precise observations of this UV radiation cannot be carried out from here on Earth. The Sunrise Observatory floats at a height of 35 kilometers in the Earth's stratosphere. From that unique vantage point, the observatory's telescope provides researchers with high-resolution images of the surface of the Sun.
At that altitude, 99% of the air is below the observatory. You're almost in a vacuum, very close to outer space. The sky is black, not blue, and there's almost no atmospheric turbulence. You can take very high-resolution images. Our goal was to achieve a special resolution of less than 50 kilometers of the solar surface, and we succeeded. You could compare that to being able to discern a 1 or 2 euro coin from a distance of about 100 kilometers.
Sunrise thus provides the scientists with a view of the Sun undisturbed by the Earth's atmosphere, at a fraction of the cost of a space mission.
By the way, the death of a star can take many different forms. It depends on its final mass. When the final mass is more than 3 times that of our Sun, you get a gigantic explosion. The famous supernova we're all familiar with. And what remains? Well, a small black hole that can't be seen. Next, you have stars with a mass somewhere between 1.5 and 3 times that of our Sun. You also get a gigantic explosion, but that will leave behind what's called a neutron star. That's visible through a telescope, but it's very small, only about 15 kilometers in diameter. It's very bright and as dense as an atomic nucleus. Then there's the third possibility, which is what will happen with our Sun. The Sun will shed its outer layers, leaving behind a white dwarf, which glows with a bright light. And what's it made of? Almost entirely of carbon, basically like a diamond. But it doesn't sparkle like a gemstone. It's just a clump of carbon atoms.
Based on their observations of the stars, researchers have also drawn conclusions about the history and the future of our Sun. The study of aging stars can serve as a blueprint to better understand the Sun.
How do we know so much about the birth of the Sun? We know it from our observations of other stars. We can observe them in various places, and not just one star, but many of them. We can observe places where stars are being formed. But we also see stars that are dying, that are bloated, that are the red giants. We can observe the moment that they shed their outer layers, which is very beautiful viewed through the telescope. You can see the Planetary Nebula, as well as the core, which is the white dwarf. First, it's enclosed in layers. Later, the layers are shed and only the white dwarf remains. And you also see ones that have run their course, that are nearly extinguished.
The researchers are on a never-ending journey to the limits of human knowledge. They are searching for the blueprint of the universe. The pace of research has accelerated, as have the insights it offers us. The more deeply scientists venture into space, the more information they gather about our planetary system. To carry out direct observations of the Sun, researchers have also been developing ever more precise and specialized instruments. Einstein Tower is an observatory on a hill in the city of Potsdam, just outside Berlin. Built by architect Erich Mendelsohn in 1920, it houses what was once Europe's most important solar telescope. The telescope was designed by astrophysicist Erwin Finlay-Freundlich to test Albert Einstein's recently developed theory of general relativity. That accounts for the structure's name, Einstein Tower. While researchers at the observatory did not succeed in proving the theory of general relativity, Albert Einstein received a lifetime appointment as chair of the board of trustees of the Observatory Foundation.
Now we basically have to move the dome so that sunlight strikes the mirror. This mirror catches the sunlight. You can see an axis here, parallel to the Earth's rotational axis. So when the sun moves across the firmament, we can retrace that movement with this mirror. It sends the light to the second mirror, whose only purpose is to direct the light vertically downward into the telescope. The light then strikes a lens that's 60 centimeters in diameter. It has a focal length of 14 meters and produces a solar image that's about this size, 14 centimeters, down in the Optical Laboratory, the laboratory in the basement of the Einstein Tower.
The mirror under the dome directs the sunlight into the telescope, located inside the tower. The height of the tower, in turn, determines the focal length of the telescope.
Then the sunlight can pass into the basement laboratory.
The telescope rests on its own foundation to protect it from vibration. It's surrounded by the tower, which serves as a protective shell. The sunlight passes through the tower down to the basement.
The light then hits this mirror, which redirects it over this optical bench, where we can carry out tests on instruments. Then the light strikes this wall. This is the Spectrograph Gap.
The basement of the tower is where the actual research laboratory is located. Once the light arrives here, it is diverted again. The spectrograph lies at the heart of the observatory. It's where sunlight is separated into its individual wavelengths. By analyzing the spectral lines, scientists can determine the chemical composition of the sun. The Einstein Tower and its solar telescope belong to the Leibniz Institute for Astrophysics in Potsdam. Researchers here are still working with the data that has been collected over decades of observation.
Here you see the times of day and which cameras were observed. These are basically the Einstein Tower's laboratory reports. We can still use the data recorded here and analyze it. These here are the photographic plates. Every day, weather permitting, photographs were taken of the entire solar disk. So here you can see sunspots extending in a row along the equator from east to west. And here are similar groups that extend from the edge of the sun here to the middle of the sun.
The telescope in Einstein Tower is still fully operational. Even today, instruments to observe the sun are developed and tested here. Nowadays, though, solar observations are conducted with far more modern instruments, and they have moved to areas that are more remote, far from any city. Gregor, Europe's largest solar telescope, is situated on a volcano on the Spanish island of Tenerife. High above the cloud cover, the calm and clear air offers perfect conditions for a solar observatory. Gregor was co-developed by researchers from the Institute for Astrophysics in Potsdam. The telescope's large main mirror can obtain solar images of unprecedented quality and resolution.
In a solar telescope, a large mirror is key. This one is 1.5 meters in diameter. You need a large mirror to collect a lot of light, which we need to carry out our precise measurements. The larger the mirror, the more high-res your solar image will be.
Gregor first set its sights on the Sun in 2012. Since then, it's been supplying images that would be impossible to obtain in Germany.
Atmospheric conditions are the most important criteria for deciding where to build a solar telescope. First, the sun has to shine. The more often it shines, the better. That suggests it's best to go south, where you have sunnier weather conditions than in our northerly latitudes. A mountaintop is also good. The higher you are in the Earth's atmosphere, the better and clearer your view.
A new generation of solar telescopes are already in planning. One is EST, the new European Solar Telescope. Its main mirror will be 4 meters in diameter, making it Europe's largest solar telescope. This high-resolution telescope will allow scientists to investigate fundamental processes of the Sun in greater detail. The researchers hope to obtain new insights into the Sun, from its deep photosphere to the upper chromosphere.
By the way, did you know that our sun vibrates? That's because our sun, at about 5,000 degrees Celsius, is molten, a liquid, all the way through. Imagine our sun is an enormous droplet of water. Like any drop of water, it can vibrate under conditions of zero gravity. Of course, these vibrations are so small that we can't see them from here on Earth. They can only be seen using very special instruments that observe the sun in great detail. Since other stars are about as hot as our sun, they vibrate in much the same way.
In carrying out their research, astrophysicists have embarked on a journey into infinity. Our own Milky Way contains more than 100 billion stars, and our solar system is just one among many. But it is the study of our own sun that lies at the foundation of astrophysical research. Our sun forms the basis for understanding other stars.
Is there such a thing as the perfect star? The star that makes biological life possible? Yes, there is. But to understand why, we first have to look at a completely ordinary star. For example, TRAPPIST-1. That's the star we see here on the far left, which was discovered quite recently. It's a red dwarf star. And what's also interesting is that it has many planets. 7 planets, as you can see here. But only 2 are located in just the right spot. These ones here, which, as you can see, are blue. That's because they have liquid water on them. In other words, their surface temperature is somewhere between 0 and 100 degrees Celsius, which is where life can arise. The other planets, which are further out, are already too cold. They've only got ice. And the ones that are further in are too hot. They're already more than 100 degrees Celsius, so life can't emerge there. What we need are planets in the habitable zone. The big problem with TRAPPIST-1, and indeed all red dwarf stars, is that they emit huge blasts of radiation. That radiation reaches the planets and would extinguish the basis for life life there. So what we need is a good-natured star in the middle, what's called a G-type star. Our own Sun is a G-star, a very happy and content star that's been burbling away without any outbursts for many billions of years. Plus, the Earth is situated right in the middle of the habitable zone. In that sense, the Earth and Sun are perfectly situated for the emergence of biological life.
For many years, scientists were puzzled by the dark spots in our Milky Way and in other galaxies. A dark band divides the Milky Way into two, clouds of such density that the light of the stars can't pass through it. But it is these clouds that contain the matter from which new stars can emerge. These star factories can give rise to thousands of new stars. The Orion Nebula in the Milky Way is the closest such star factory to Earth. This stellar nursery gives birth to very massive stars. The enormous Hydrogen Nebula is 1,344 light-years from Earth, just around the corner in galactic terms. The Orion Nebula is about 3 million years old. In its center lies a collection of young stars. Using infrared and X-ray telescopes, astronomers have been observing the birth of new stars in this galactic nursery in what is almost a live performance. Our galaxy, the Milky Way, contains about 1,500 such nebulae. They are all regions in which stars are born. The basic principle is always the same. The death of massive stars promotes the birth of a new generation.
When a star dies, it gives back a part of its mass to the interstellar medium. In the case of the Sun, that would be the entire outer layer. That would be half, perhaps more than half, that will return to the interstellar medium. Stars that are even more massive return more of their mass. For example, stars that are 10 or 20 times heavier than the Sun. Those stars don't live 10 billion years. They live only around 100 million years, or 10 million years, or even less. They're very short-lived stars. In the end, they explode. They're torn to bits. Just a small bit remains, the core. The outer layers are thrown off at enormous speed.
Dying stars return part of their mass to the interstellar medium. Ever since the Big Bang, this dust comprised of what were once stars gives rise to new celestial bodies. In particular, planets that bear a resemblance to Earth.
Are all stars only children? No, definitely not. Many stars have siblings. Most have one sibling, in fact. Let me explain. It all begins with that enormous cloud of gas, which collapses on itself. It begins to rotate. The laws of physics have to maintain that angular momentum despite this gravitational collapse. That's accomplished most easily with two stars. Let's sketch this out. On the one side, we have one star. They don't have to be the same size. This one is, for example, smaller. To maintain the angular momentum, the two stars need to revolve around each other, like this. So now the question is, where do the planets emerge and where do they revolve? Well, there are two very different possibilities. The first is a planet revolving in the direct vicinity of a star, as I'll sketch here. Or you could have a planet emerge further away, which revolves around both stars. As you can see here, I've drawn a somewhat wobbly line. Why is that? Well, while the planet revolves here on the outside, the two stars move here at the center. So the planet is constantly subjected to slightly variable gravitational forces. That's why the orbit isn't a perfect circle. The same thing is happening here. This planet revolving here is subjected to the gravitational gravitational pull of the other star, from here, here, or here. So its orbit also has bumps and bulges. Bumpy orbits such as these are very unsuited to life, since they mean that climate conditions will be highly variable. In other words, small bacterial life forms might arise that aren't terribly bothered by climate conditions. But higher forms of life, such as human life, need a very stable climate over millions of years. That's exactly what all these planetary orbits don't provide. And that's the reason why it's very unlikely that life would emerge in these binary star systems.
One of the most famous scenes in Star Wars also drew inspiration from a binary sunset. In the past, scientists believed that planets did not exist in binary star systems. Meanwhile, however, their existence is well documented.
Binary star systems are relatively common. There are also systems with more than 2 stars, 3 or even more. That's because when stars are formed, it's usually not just a single star. When one of those enormous clouds collapse in interstellar space, a great many stars are formed, an entire group of stars. And if 2 stars happen to be near enough to one another, and if they're not moving terribly fast, gravity will draw them closer together. And then they'll begin to revolve around one another.
Astronomers estimate that up to 70% of all stars in our galaxy are part of a binary or multi-star system, most probably have their own planetary system. And it could well be that some of these systems contain exoplanets revolving in a stable orbit. A planetary system such as ours, with just one central star, might be an exception within the infinity that is our universe. Our sun, an enormous ball of fire, a nuclear reactor brimming with seemingly endless energy, a star that we experience directly here on Earth, and an object whose characteristics and peculiarities we continue to investigate and explore. And yet, our sun is just one star among billions in our galaxy. It is nothing but a blip in the endless expanse of the universe, and like every star in the cosmos, the sun will one day be extinguished.
What will the end of our sun look like? Well, for the next 20, 30, 40, maybe 50 million years, nothing at all will happen. The sun will just continue to burble along as it does now. But as it does, it will expand very, very slowly, and it will grow warmer very slowly. Temperatures on the Earth will continue to rise until they reach about 100 degrees Celsius, about 1 billion years from now. By then, our oceans will have evaporated, and that will spell the end of human life. But, as I said, that's 1 billion years from now, so that's nothing to worry about. But that won't be the end of our sun. It will continue to expand and grow hotter until it finally consumes the Earth. And that will be the end of our Earth. Eventually, the sun will cast off its outer layers and collapse, and a small white dwarf will remain. Those outer layers will be incorporated into other clouds of gas a great distance away. They'll also contain elements that make up our bodies. These clouds of gas will eventually collapse too, giving rise to new stars and new planets. And a new cosmic cycle will begin.
We are surrounded by infinity that is beyond human comprehension. A universe in which the sun and our solar system are nothing but specks of sand in an enormous ocean. Just like our sun once emerged from a nebula of matter, in the end it will cast off its outer layers and be reabsorbed into this strange cosmic landscape. A landscape of light, gas, and stardust, formed and shaped by cosmic wind and radiation. Some 6 billion years from now, when our sun finally runs out of fuel, when its hydrogen supplies have run dry and its celestial fire has been extinguished, then it too will contribute to the eternal renewal of the universe.